Alright, hey y'all, it's Mr. Kyle Myers Mathematics, and let's just jump right into it. We are using the Squeeze Theorem, as in, kill me now, to find the limit of each of the following sequences. So, number 41, cosine of 1 over n minus 1 all over 1 over n. I don't know who comes up with these problems. These are ridiculous. Alright, let's see. So if this is A, and if they don't say where it starts, we assume it starts at 1. So in is 1. And let's see what happens here. So this is going to be the cosine of 1 minus 1 over, well, actually 1. Okay, so that's not too bad yet. The cosine of 1, well, we're in radians. Because if they don't say, then we just assume we're in radians. We're in radians, so pi thirds. Pi thirds is about 1 radian. Cosine of 60 is about a half. So that's a half minus 1, so negative half. About a negative half. Negative 0.5. That's going to be fairly close, probably. All right, what about n equals 2? Okay, this is where it starts to get a little interesting, I think. Cosine of 1 half minus 1 all over 1 over 2, which is 1 half, or 0.5. Cosine of a half. So it'd be a half of pi thirds, which is pi sixth. Rough estimates here, because pi is about 3. So 3 over 6 is about a half. Cosine of pi 6, that's root 3 over 2. Root 3 is about 1.7. Half of that's about 0.85. 0.85 minus 1 is negative 0.15. And then we take half of that. Well, no, we're dividing by half, so actually timesing it by 2. So negative 0.85 doubled, which would be negative 1.7. All right, check me on that math if you want, but I'm just gonna lock that in. Negative 1.7. So it looks like it's getting more negative. Well, interesting. All right. Well, what about cosine of 1/3? All right, cosine of a third. Oh, but you know what? This is gonna get closer and closer to 1, right? Because the fraction's going down, so it's less and less radians. So we're getting closer to the cosine of 0 over time, and the cosine of 0 is 1, and then 1 minus 1 would be 0. And then all of that's over, well, a larger and larger number in the denominator. So actually, it seems like it, I'm not sure actually. This would be over a third. Over a third. What if we could just we could just use L'Hopital's? Because I kind of want to just figure out what the answer is. I don't like Squeeze Theorem. I don't know if I've made that really obvious yet, but like I really don't like Squeeze Theorem. I would rather light myself on fire. So let's see if we can just get the answer. That way we know what we're shooting for. So, okay, so when they say find the limit of each of the following sequences, or if they say it a different way, they might say see if the sequence converges or diverges. If they say that, they're also looking for the limit as it goes to infinity. And if they don't specify the limit, then you assume it's a limit to infinity. There's a lot of assumptions in math, which is kind of weird because I've heard it said that like don't assume anything in mathematics, like, but we actually do. There's like certain things that are safe to assume, and then other things that are not safe to assume. And I'm sorry, it's just the way it is, I guess. It's like sometimes it's okay to assume things because there's like established default things. Like radians is the default thing. But sometimes it's not, depending on the context. So, you know, it is what it is. The limit as all of that goes to infinity. So we could actually use L'Hopital's, I think, because it's something over something. Cosine of 1 over n. Is it going to write the s? There it goes. It's just being a little slow. 1 over n. What'd you call me? All right, over 1 over n. So I believe we could use L'Hopital's. Yeah, because if we try to plug in infinity, 1 over infinity is 0. Cosine of 0 is 1. 1 minus 1 is 0. So you get 0 on the top, and then if you plug in infinity on the bottom, you get 1 over infinity, which is also 0, so you get 0 over 0. So that's indeterminate, which means we can use L'Hopital's rule. So, and if you're watching this at double speed, you are crazy, because I already talk fast enough as it is. So, if anything, I would think like half speed or 0.75 speed. But here we go. So let's take the derivative of the top, derivative of the bottom. I know this is like a video on Squeeze Theorem, so you can skip ahead a little bit if you want. I normally don't do a lot of editing, if you haven't noticed yet. So I don't know to what point you would need to skip to in the video, but if you want to skip to like the answer using Squeeze Theorem, you're welcome to do that. It'll hurt me, but if it'll help you, I'm willing to take one for the team. It's the real ones that stick it out to the end though. So thank you, real ones out there. So so derivative of cosine is going to be negative sine. So let's put a little parentheses here, I guess. I don't know why. Just because I felt like it, I guess. Negative sine. Yeah, it's being really slow. I wonder if it's because I have a bunch of other things on this board still. Like I've used this Microsoft whiteboard for like all the other videos in this series on series. So like it's got quite a bit on it at this point. So I might have to start a new board. But let's see. So negative sine, whatever in. And then we take the derivative of the inside. And that's going to be into the negative 1 power. Into the negative 1 power would be pull the negative 1 out. And then it's in, and then power minus 1. It was already a negative 1 power. So negative 1 minus 1 is negative 2. So it'd be negative into the negative 2 power. And then that would go away. Constants have a derivative of 0. And then the same thing on the bottom, which actually, because I already know that the derivative is going to be negative into the negative 2, I can just go ahead and simplify it a little bit to negative 1 over n squared. Clean it up a little bit right off the bat. And yeah, so there we go. So the bottom still would be infinity, which is kind of a problem. Oh, you know what, though? So it's n squared, but like, well, wait a second. No, it cancels out. No, it doesn't. Yes, it does. No, it doesn't. Yeah, because that would be... Yeah, it cancels out. Because that's negative into the negative 2. That's negative into the negative 2. They would, yeah, they would cancel out. What am I doing? Okay, so then this is the limit of... We'll just yoink that negative out. There we go. Negative limit of the sine of 1 over n. And what is that going to be? Is that 0? Because we're going to infinity, right? Sine of 1 over n. Yeah, because n is going to be bigger and bigger and bigger. Sine is a wave. 1 over n would still be wavy, wouldn't it? Or would it not? Because n would be, when n is 1, we would have the sine of 1, which is about pi thirds, right? So about 60 degrees. And then it's just going to decrease from there. So it's starting at about 60 degrees, and then it's decreasing down to 0. And then eventually it would get to 0. And that's what that graph would look like. Yeah, so it would basically just kind of like go like that, and then level off at 0. So yeah, that would be 0. So the answer, it looks like it's 0. It looks like the answer is going to be 0. Okay, cool. So now we have the answer, and then we can figure out how to squeeze it. So in order to squeeze it, we need to figure out what's above it and what's below it. So if you have to do this without a calculator, I'm sorry. That's terrible, and your professor's crazy. So, but if you want to evaluate these numbers, I'm not going to try to evaluate this one because, yeah. So, anyways, but this is it looks like it's going to be like a negative, and then it looks like it's getting bigger, but then maybe it's going down after that, because we know the answer is going to be 0, right? So like, yeah, let me go ahead and type this in. So let's go ahead and go over to the graph. And if you can't use, so like, little note for people that are doing this, that that are being told to do this without a calculator, you could just try values and just keep typing in values to make a t-chart, which is what I've showed you with the table here so far. So like this is what you would do without a calculator, is you'd make a t-chart and just kind of like compare values, and then you would need your above and your below, right? So if you'd have your below, right? And that below function would need to always be below the a function as you're going to infinity, and then you'd have your above function, which could be like a c maybe, um, and so on and so on. So we're actually that what you would have to do by hand is you would have to just compare functions and just kind of like go based off of what kinds of functions you know work. And this is one of the reasons why I don't like Squeeze Theorem, is because I do okay with Squeeze Theorem, but that's because I just memorized a bunch of graphs. Like I just memorized a bunch of graphs. But I don't really know a better way to do Squeeze Theorem other than just like if you have a large library of graphs just floating around in your noggin, then it's just like how do you even come up with the graphs to use for the above and belows? It's kind of crazy that they expect people to use Squeeze Theorem, and it's not even like it works that great. Like I was able to do the whole thing just using L'Hopital's rule. It's way easier using L'Hopital's rule. Anyways, just I don't like it, obviously. Um, so we're gonna type in the graph. So I'm gonna bring this over here. Hold on. Here we go. Yeah, that way you guys can see this too. Okay. And then what was the graph again? I forgot. Let's bring this over here. Okay, so we'll have f be our regular function, then we'll have like g and h be the above and below. Okay, so cosine of, and Desmos defaults to radians, so you don't have to worry about that unless you need to be in degrees, and then careful because it will default to radians. Every time you close it and open it up again, like it won't save your settings because it's just a web page, right? So like, and you're not logged in or anything. Oh, whoops. I like talking and writing at the same time, which is not working out really well. Okay. And I don't need an in slider. Thank you, though. Ooh, sliders sound really good now, actually. Maybe I'll have a slider for dinner. What is... No, I don't want a curly base bracket. You peasant. All right. So we have this, and no, I don't want a fraction over the whole thing either. Why are you doing this to me? Okay, here we go. So 1 over x. Aha! And it is 0. Look at that. Lo and behold. Okay, cool. So it's a little crazy there. Look at that. This is pretty cool. Check this out. Oh, no, I don't want to do that. Nope, I don't want to do that. I don't want to do that. Look at this. Oh, I love it when you can... No! Stop it. Watch this. Boop. Never ending. That's so crazy. Some of these graphs are just so crazy. All right, so it's definitely... Oh, now it wants me to plug in my laptop. Okay, so it definitely... I will just roll with it. It probably won't die. It probably not. Probably not. So so it's definitely coming up from the negative, and you can kind of see like, so I did 1 and then I did 2. Maybe I did something wrong because with 1 I got negative 0.5, which actually that was about right. But then the other one I got like negative 1.7. So I did something wrong on the in value of 2. So I apologize. I was terrible. It was root 3 over 2. I think I was trying to do too much mental math, and that was what happened there, so sorry about that. Maybe it was negative 0.7? No, because that would have been lower. I don't know, guys. I don't know what happened there. I messed up with the mental math there, because it is less negative at 2. So, you know, ixnay on this. Hold on. Yeah. So, this was negative IDK. Negative IDK LOL. Yeah, because I messed up at some point doing my mental math there. Let's see. So, where is it? This thing? Yeah, there we go. Okay. So, here's our graph. It's a nice graph. We need a below and an above. The above is not hard, actually, because basically anything that will have a limit of 0. So how about this? G of x, 1 over x. Problem solved. Easy money. Okay, so there's our above. I wonder if below I could just get away with this. Hold on. Negative 1 over x. Is that? Problem solved. There we go. Okay, that works. 1 over n and negative 1 over n. Yeah, because check this out. Yeah, the purple is always below. Now, if you need to prove it using more rigorous methods than looking at it on Desmos and just doom scrolling to the right, like I'm doing right now, then what you would need to do is um, you would need to basically like write out that the purple function. So let's call the purple function. It's below the other one, so we'll call it the b sub n. So you would say b sub n is less than or equal to f of x, or the a sub n for all in, and you would have to cook it out. So you'd have to figure it all out. And then same thing with the g, right? So that would be our above function. We call that c sub n maybe. C sub n is greater than or equal to a sub n for all n. That one would probably be a little easier to prove. It's definitely visually easier to prove because the other one is always negative and the other one's always positive. So you could actually just say that, like, hey, it's always positive, the other one's always negative. So a number that's positive is always going to be bigger than a number that's negative. So yeah, you could probably just do that. That'd be a little easier. But then the other one, yeah. So yeah, you could basically just say at this point we're basically done, guys. What we would do is we'd say, okay, so b sub n, our below function, b sub n is negative 1 over n, and then c sub n, that's our above function, is just positive 1 over n. And yeah, so you would just basically, you would get into all the formalities, which is, I did this in the last video. I don't know if I have space for it on this video, and I kind of want to like cap it here. One, because it's about to die, and two, because the video is starting to get kind of long. But at this point, we're basically done. You would just say, okay, so b sub n is less than or equal to a sub n, less than or equal to c sub n for all n, and the limit as b sub n goes to infinity is 0, and the limit as c sub n goes to infinity is also 0, because it's the harmonic and the negative harmonic functions. So those are just known functions that go to 0 as they go to infinity. Or you could use rational functions. You could say, oh, it's a rational function, and the horizontal asymptote of the rational function would be 0. So that's how we know the limit would be 0 as it goes to infinity. However, your professor needs you to answer the question at that point. And that's basically it. And then you would just say, hey, that because b sub n and c sub n go to infinity, and because the b sub n and c sub n are above and below, therefore a sub n's limit would go to 0 also. And then you would stop there. All right, awesome. Well, we'll go ahead and cap it here and check out the 5 math mistakes everyone makes and how to avoid them. And that's on my website, myersmathematics.com. You can check that out in the description down below. See y'all in the next video. Blessings.